in this section, I'm going to be discussing the phase one of the simplex algorithm. So first, let's write down the linear program that we're trying to solve. So we have minimize linear form C transpose X, where X satisfies a set of equations A dot X equal to B, and X is non-negative. So this is my linear program. We want to find the X that satisfies this set of equations, also minimizes this like a cost function. Okay. So in order to use the simplex algorithm, we need to have a simplex tableau for this. So let's say, okay, input. What's our input? Our input is the matrix A, the right-hand side B, okay, and I'm going to put this objective function in the equation. That is, I'm going to write Z equal to C transpose X, or C transpose X minus Z equal to 0. So I'm going to add this at the bottom. And then this is the column corresponding to Z, minus 1 and 0. Okay. So I wrote this this linear program in a tableau format. Now, the purpose of phase one is to take this and find a simplex tableau for this, of this form, something that looks similar to that. So here I have A bar, and here I have B bar, and here I have C bar, and here I have the same Z minus theta. Okay. It looks almost similar to that, except this is a simplex tableau. And the requirement, simplex tableau, is defined by, first, the right-hand side B bar is greater or equal to 0. 2, the identity matrix is in A bar. And by this I mean the column of the identity matrix are somewhere in here. So 1, 0, 0 is somewhere in here, 0, 0, 1, 0, 0 is somewhere in here, and so forth. Not in the same order, but all the columns are somewhere in there. And 3, C bar of I is equal to 0 for I basic. This where the columns are called basic columns here. Where the column of the identity matrix are, we call those basic column, and the other ones we call them non-basic column. So 3 is C bar of I is equal to 0 when I is basic. That is, under the identity matrix, the coefficients are all zeros. Then we call this a simplex tableau. So, and once we have a simplex tableau, then we could use the simplex algorithm to optimize this number here, theta. So this is the mission of phase one, is to take this general system and transform it into a similar system, but it is simplex tableau that satisfy these conditions. So how do we transform a general system like this into a simplex tableau like this with this condition over here, 1, 2, 3? So first, step one, this condition here, right hand side being greater or equal to 0, we can achieve it very easily by just, in the begining, we're just going to make b greater or equal to 0. All right. In here, we're going to make b greater or equal to 0. We're going to go equation by equations. And if the right side is negative, we just multiply the both sides by -1. So that's easily achieved. And then step 2, we're going to solve a new linear program, which I'm going to call phase 1 LP. Okay, and it's defined as follows. We're going to minimize E transpose W subject to A dot X plus IW equal to B, X greater or equal to 0, and W greater or equal to 0. Okay, so this is a new linear program. So what we did from here, we added IW. That means every equation we added one variable. So W1, W2, and so forth. So W is W1, etc., Wm. As many variables are constraints here, equations. Okay. And we are requiring that the W also is greater or equal to 0. That means every one of them is greater or equal to 0. And here we are minimizing E transpose W. Okay. Which is just W1 plus W2 plus etc. plus Wm. Okay. These are called artificial variables. Okay, so this is the program that we're going to solve in step 1. Okay, let's do some facts about this program. So I'm going to erase this. So facts. This P1LP is feasible. That's the number one fact. In other words, there is X's and W's that satisfy this set of equation. Namely, one of them is trivial, is X equal to 0 and W equal to B. Okay? So that satisfies this set of equations. And remember, we made B greater or equal to 0. So W is greater or equal to 0. So this program is feasible. Unlike this one, the LP, we still don't know whether this set of equation is feasible. In other words, are there X's that satisfy this set of equations? But this one we do know. So 2, here we are minimizing the sum of these W's, and they are all greater or equal to 0. So this min is greater or equal to 0. Okay? Because every instance is greater or equal to 0. So here we have a linear program that's feasible and is bounded from below. So in other words, this minimum cannot go to minus infinity. So therefore, 3, P1LP has an optimal solution. Okay, and I'm going to call it X star W star. Okay. Fact 4 is that if E transpose W star is bigger than 0, right? So this min can only be 0 or something positive. So if E transpose W star is bigger than 0, then our LP is infeasible. meaning that there is no x satisfying ax equal to b, x greater than or equal to 0. So there is no sense solving this problem. And it's obvious, because if this was feasible, then you could take the x feasible and you plug it in here with w equal to 0. And that will give us a minimum equal to 0. So this is an easy fact. Fact 5, if E transpose W star is equal to 0. Okay? So the sum of the W star of I is equal to 0, and all of them are greater or equal to 0. That means each one of them is equal to 0. So that means W star itself is equal to 0. And if W star is equal to 0, then AX star is equal to B, X star greater or equal to 0. Which tell us then LP is feasible. Okay, so in this case, we have a solution to our system of equation in the LP. And of course, we need to find the solution that minimizes it. So in this case here, we do need to have a simplex tableau for this. Okay. Now let's do fact 6. This linear program has a starting simplex tableau. Namely, it's the following. A, I, B. Okay, so I have A, I, and B. And then here, Z, let's take Z equal to E transpose W, which is equal to, so from here, E transpose W is equal to E transpose B minus E transpose AX times X. Okay? And in other words of writing it, we write it like minus E transpose A X minus Z equal to minus E transpose B. Okay? So in here, I get minus E transpose A. Here is zeros. And then here, minus 1 for the Z, the objective function. And then here we have minus E transpose B. Okay? So now, this is a simplex tableau for this problem, for the P1LP. Why? Because, first of all, the B was greater or equal to 0. We took care of that. And here I have the identity matrix. It's right here. And in my objective function, I have 0 under the identity matrix. So this is a valid simplex tableau for this. So we could start from this simplex tableau and then use the simplex algorithm to solve this problem. So now, before we see how we're going to solve this problem, let's ask the question is, why solving this problem help me with this problem? Remember, our objective is to find the simplex tableau for this. Here, when we start, the basic variables are over here. All right? That's where the identity matrix. Those are the basic column. Let's say that we were able to, through the simplex, got this one, A bar. Here, of course, go B inverse. Here, 0, 0, 0, This is B bar, right? And then here whatever it is, -1 minus theta bar, right? Let's say we, through the simplex, we were able to solve the problem, and this is the final simplex tableau. And then also suppose that my basic variable are over here. They are no longer, in other words, the artificial variable are no longer basic. It's the x's that are basic. If I get something like this, then I did find a simplex tableau for this. Because why? All I have to do is ignore this area here and ignore this objective function, right? So I will ignore this. I'll just keep A bar and B bar, and then I bring in the objective function C. C bar transpose is equal to C transpose minus C beta transpose times B inverse of A. Remember that formula. So we plug it in here. C bar transpose, and then here is minus 0, 0, 0, 0, minus 1. And here the theta bar is just C beta transpose times B bar. Right? Minus C beta transpose B bar. And this is now a simplex tableau for my LP. Okay? Because it satisfies all the, first of all, it's an equivalent system to this, and it satisfies all the characteristics of the simplex tableau. So that's the hope, that we, by solving this, we get this. Okay, that all the artificial variables leave the basis and only the x columns are basic. Okay, so this is our phase 1 LP. Okay. Now, we don't know whether this problem is degenerate or not. So we're going to use the technique that we analyze in the section of degeneracy. We're going to attach the identity matrix here, and we're going to solve the lexicographic P1LP. And we know that this linear program is non-degenerate, and therefore the simplex, using the simplex iteration, it's going to converge in a finite number of steps, and I ended up with a final simplex tableau that looks like this. We have A bar here, of course, under the identity will be B inverse, B bar, and B inverse, and then this is the objective functions. Okay, so this final simplex tableau is the final simplex tableau of the lexicographic P1LP. It's also the final simplex tableau for the epsilon LP. And there, to determine for what epsilon, we just look here in each row. Each row define a polynomial in epsilon, and we find the positive roots. And then we have an interval where this would be the final simplex tableau for all epsilon LP for each epsilon in that range. And of course, it's also the final simplex for the P1 LP. And all I have to do is take this part off, and that will be the final simplex tableau of the phase 1 LP. So now all we have to do now is analyze the results. And let's take, first of all, there are many cases. So let's take the best case scenario first, case 1. The best case scenario, remember that the objective of phase 1 is to get a simplex tableau for the linear program. So the best case scenario is, well, initially when we start, let me do it here, when we start, our basic variable are over here. This is what the identity matrix. So this is my basic column. Let's assume that for this case that all this variable, this artificial variable, left the basis, and my basis is somewhere in here. All my basic variable is in this range here, not under the B inverse. Then we have a simplex tableau for this, for the linear program. Why? Because I'm going to take A bar, and I'll take B bar, and then in here, of course, since the basic variable are in here, I have the identity matrix in here, and the B bar is greater or equal to 0. That's good. And then now I bring in my objective function C transpose X. All right? And here, the formula for C bar, here goes C bar transpose, and here my -1 minus theta bar. All right, so now C bar transpose is just equal to C transpose minus C beta transpose A bar. Or if we are doing the revised simplex, it's just C transpose minus C beta transpose B inverse A. Okay, that's what goes in here. Here, all we are doing is canceling. We're putting a 0 under this basic columns. So we put that here, and the theta bar is just C beta transpose B bar. Okay, and my basic variables are going to be right here, and we are done. Let me erase this. Before we leave this case, since all the basic variable left the basis, okay, then when we for the basic feasible solution, we're going to set the non-basic variable to 0. So all the artificial variable are set to 0. So the lex min, or E transpose W, that's equal to 0. Because none of these W are basic, so the minimum is going to be 0. And remember, in phase 1, when E transpose W, the minimum is 0, that means the corresponding linear program is feasible, which is A dot X equal to BI X lexicographically greater or equal to 0. This is feasible. Okay? We have an X, so satisfy this A dot X equal to BI. Remember, X is a matrix. So that's that. Then, also for the epsilon LP, the minimum of E transpose W, I say W epsilon, is equal to 0. So therefore, A dot X equal to BI times 1 epsilon, etc., epsilon to the power m, X greater or equal to 0. This linear program, this is feasible for epsilon less than r and greater or equal to 0. Okay, and also our original problem, A dot X equal to B, X greater or equal to 0, this is also feasible. Okay, so this is the best case scenario. Okay? When all the basic variables, originally they were artificial variables, they left the basis and they are over here, then we just disregard all this and form this simplex tableau for phase 2. Now we can go to phase 2 with this tableau and optimize the objective function that we had, C transpose X. Now let's do the second case, the opposite of this case. So case 2, I have a mixture. They didn't all leave the basis. I got some that's still in the basis, and I have some basis over here. So in this case, I have some basic variable here, and I also have some basic variables here. Okay. That's the second case. So I'll state it that way. Some artificial variables are in the basis, are basic. Okay. So what can we say, first of all? So what can we say about lex min of E transpose W? What can we say about the lex min? Since the basic variables, since I still have some basic artificial variable, when we set the non-basic variable to 0 and the basic variable equal to the right-hand side, so some non-basic, some basic artificial variable are going to be equal to the right-hand side. But each right-hand side is strictly lexicographically positive. So this is strictly lexicographically positive. And remember, is when the objective of phase 1 is strictly positive, that means the corresponding linear system is infeasible. So A dot X equal to BI X lexicographically greater or equal to 0. This is infeasible. Okay? And the same thing for the epsilon. The epsilon 2 is infeasible. So I have the minimum of E transpose W here of epsilon is bigger than 0. So therefore, the A dot X equal to BI times 1 epsilon, etc., epsilon to the power m, and x greater or equal to 0. This is infeasible. This set of equation is infeasible for epsilon less than r and strictly bigger than 0. For the reason that this E transpose W is greater than 0. Okay? And we know what r is. Any epsilon that's between these two values, if you plug them in here, we get a system of equation that has no solution. Okay. Now we have shown that the lex LP is infeasible, and also the epsilon LP is infeasible. So now we look to the LP itself. Is it infeasible or not? So we have, this is the P1 LP final simplex tableau. Right? It's obtained from the previous tableau without that matrix over here. Okay. And now I did some rearrangements here. So in here, we are in a situation where we have some artificial variable still in the basis and some X column basic. So this is some X column basics, and this is the basic W columns. So I made, first of all, I made column permutations and row permutations. So I have it look like this. But in general, if you let beta be the basic X column indices, beta bar the non-basic column indices, gamma is the basic X rows, it's the rows where the basic X are, and gamma bar where the basic artificial variable rows are, then these matrices are defined this way. So this will be A bar of gamma beta bar, this will be A bar of gamma bar beta bar. This stays the same, 0i because it's basic, and then some matrix here and some matrix here. So this is RB inverse. Okay, now the corresponding, the initial simplex tableau will be like this. So here are the basic axes, the non-basic axes, and this is the artificial variables. Okay, so this is, by doing this permutation, we don't lose anything. It's just to make our discussions easier. Okay, so now case 2a. So this is the P1 LP, phase 1 LP final simplex tableau. So we look to this theta 0. So this case theta 0 is not 0. Okay? So which means that the minimum of E transpose W is strictly positive. All right? So therefore, the LP is infeasible. Okay? So we saw that earlier. Whenever the minimum of phase 1 is bigger than 0, our LP is infeasible. Here, no phase 2. Okay? So that's that case, case 2a, very simple case. Now, case 2b, theta 0 equal to 0. Okay? So I'm going to erase this theta 0. I'm going to put a 0 here. Okay. Now in this case, the minimum of E transpose W is equal to 0. But how do we get the minimum? Remember, we set the non-basic variable equal to 0 and the basic variable equal to the right-hand side. So in here, the only basic variables are these ones, okay? And then we're going to set them, that's equal to E transpose. So these basic variables are going to go to this. So B bar of gamma bar. But remember, the B bar is greater or equal to 0. And here the sum of the terms is 0. So this means that B bar of gamma bar is equal to 0. Okay? So now I'm going to erase this. I'm going to put zeros here. Okay? Now, so let's read these equations here now. Now I'm going to set W equal to 0. And I'm going to read this equation right here. So here I got sum of the UI xi, right? This is the sum of UI xi. This is correspond to W, so these terms are 0. And this is E transpose W, that's 0. So this is equal to 0 for every x such that A dot x equal to B, x greater or equal to 0. This is our original set of equations, right? Just reading from this tableau. But this is the final tableau, right? So that implies that U is greater or equal to 0. Okay? We don't have no negative term here. So here, I am summing, so x greater or equal to 0, U greater or equal to 0. So I'm summing non-negative numbers, and it's 0. That means each one of these, so for every I, UI xi is equal to 0 for all feasible solution like this. Another way of saying this is that ui positive implies that xi is equal to 0 for every x such that a dot x equal to b, x greater or equal to 0. Okay? Which renders that this xi is useless. All right? It's a useless variable because it's always 0. For all feasible solutions, it's always 0. So in our final simplex tableau, if we see a 0 here and a positive here, this is the u correspond to the non-basic x columns. So if you see a positive term there, then that column is a useless column, and we just delete that column. But in practice, you don't delete the column, because deleting a column is a messy process. All you have to do is tag it and then never bringing it to the basis. But for our discussions, let's assume that we deleted those columns. So here now, I have a bunch of zeros. Okay? So here we have zeros. We have zeros over here. Okay? Now we're going to look at this rectangle right here. Okay? In my picture here, it's a nice rectangle, but the reality is the intersection of non-basic x columns with basic w rows. All right? It's a bar of gamma bar. Gamma bar is the basic w rows, and beta bar is the non-basic w rows. Okay. So in here. So suppose I have a positive term here. Let's assume that I see a positive term here. So why don't I pivot here? Okay. It's not going to change the bottom because I already have a 0 here. And here I have a 0, so it's not going to change the right-hand side. And the effect of pivoting here, it's going to replace a basic w by a basic x. And that's what I want to do. I want to get rid of the artificial variable. So a plus, so we're going to pivot there and replace a basic w with x column, with an x column. Right? And we keep on doing that till there is no positive terms here. Okay? Now I said that if there is no positive term, there is no negative term neither. Because how did we get this row here? What we did is we started with this row. Remember the initial here go E transpose and E transpose. Set of ones, right? E transpose of beta, E transpose of E transpose. This is just a series of ones, right? This corresponds to E transpose W, all right, over there. And here goes 0 and 0. So we obtained this by putting a 0 here. So what you did is we did this row minus the sum of these rows. That will be equal to this. So So this row is equal to this row minus the sum of these rows here. So in other words, 0 transpose, so this is 0 transpose right over here. That's equal to 0 here, right? 0 transpose minus E transpose A bar of gamma bar beta bar. When I do that, then I set this area here equal to 0, which I want to do because we need 0 under the basis. Okay. So therefore, E transpose A gamma bar beta bar A bar is equal to 0. So the sum of the terms here is 0. And if there is no positive terms there, then every one of them is 0. Okay? So here, after I pivot on all the positive terms, I'm going to end up with a similar tableau like this, but here is a bunch of zeros. So big 0 here. Okay. Now, let's read these equations now. What happened to, let's read these equations. So I'm going to set W equal to 0. And I'm going to read this equation. So this will be 0, and this will be what? 0 transpose times x equal to the right-hand side is 0. That's all these equations are 0 transpose x equal to 0. So this is vacuous equations. The trivial equation, they're not needed. So these equations are not needed. Okay. In other words, the simplex algorithm found out that these rows here, these equations here are redundant. They are obtained from these rows. So we really don't need these rows here. So in here, before I go there, this is our B inverse, right? So that's B inverse zero I, and let's say this is S and T, right? This is my B inverse. What goes in here? So this is the inverse of the matrix of my X columns, which are these, A gamma, beta, and then A of gamma bar beta, and then here 0 I. And this is my, so S, you can prove that S is the inverse of this. Okay, that's trivial. So here, that's why here I put A gamma beta minus 1. Okay. Okay. So now we have a simplex tableau for our LP. Why? Because first of all, this is 0x equal to 0. So I don't need this. I don't need this. Okay. And then I am left with just this. Okay. And now this, so my final, my simplex tableau, the LP, is the following, is here I, and then here A bar of gamma beta bar, okay, and my, so yeah, I get rid of this too. This is the non-basic W's. I don't need this area here, okay, all right. And here I'm going to have 0, 0. and here I'm going to have B bar of gamma. Okay, that's the top part. My B inverse is just this matrix here, A minus 1 of gamma beta. That's my B inverse. And now I'm going to bring in C transpose X, right? And here goes and I also have my beta, my BFI, right? So here goes here of course goes 0, and this goes C bar transpose, or as previous notation here we just put C bar transpose, right? And then minus 1 and minus theta bar. Okay, and we use the regular formula, C bar, that's equal to C minus C beta transpose, right? We have to put a 0 under the I here, under the identity. So C bar is C minus C beta times B inverse of A. Okay. And here B inverse of A, my A is not the original matrix, right? This is my original matrix. These were redundant, so my A matrix is A of gamma beta and A of gamma beta bar. Okay? And then the theta bar, it's just C beta transpose B bar of gamma. Okay. And this leads to a simplex, and this is a simplex, this is an LP simplex tableau and here on to phase 2. Okay. Note that here they are not in this order. It depends which order they were in initially, because remember here I kind of did a permutation of the columns, so we need to be careful with that. Okay, careful with this, the original C and mixing it with the rearrangement of these columns. But basically, so here we have we come up with a simplex tableau for our original LP. And that ends the discussion on phase 1. Okay, the next video will be the discussion of the fundamental theorem of linear inequalities and also the decomposition theorem for polyhedral sets.